Welcome back. So in this video, we're going to be dealing with the analysis of shell structures. And my apologies about the video of yesterday, but there were certain moments when I was listening to it that I couldn't hear myself. That's the previous video that I released up for plates or flat slabs, the analysis of plates or flat slabs by deriving the deflection expressions and moments expression. If you listen to that video, there are parts of the video where you can't hear me quite well. I'm sorry about that. I had my hand rested on the speaker because I use an iPad to record my videos, and sometimes I do rest my hand on the speakers, and it's just unfortunate you guys couldn't hear me. My apologies about that. So I'll try and keep my hands away from the speaker this time. So today we're going to be dealing with the analysis of shells. So shells and plates. So that is more or less one topic. We start first with understanding plates. And then if you understand plates, and then we go to shells, because there's one difference between plates and shells, and it's curvature. So plates don't have curvature, whereas shells have curvature. So if you remember with the analysis of plates, we assume that plates resist the transverse loading applied to them by bending. Hence why if you look at flat slabs, the analysis of flat slabs, we are interested in that bending, okay, to see also if the action of deflection is too much or whatsoever, the maximum deflection, what is it, etc. Whereas with shells resist those transverse loading through the internal actions that act in the tangential plane. So basically with shells, they are capable of resisting external transverse loadings by extensional action, which is what? Curvature. Okay, so today we're going to be dealing with a spherical dome, analysis of a spherical dome. We're going to derive the stress expressions that act on the dome. So this dome here, it's completely submerged in water, as you can see. I'm not going to go through the whole question. Maybe I could go. This is a hemispherical, meaning it's a half, because a hemisphere is a half sphere, a half of a sphere. A hemispherical shell of radius A is anchored at the bottom of the lake in a region where the depth of water is h. So this dome is completely submerged. So just to give you an idea, a spherical dome, if maybe, I'm trying to picture it, if you know this, or you have seen these old European buildings that have this quite weird, roofing type of structure that is all round, like an egg, or or maybe like a shell of a tortoise. So that is a spherical dome, and it's very strong in terms of resisting the applied forces towards it. You will see why I get to say that, because we can make them very thin but still very strong, which is quite amazing. And hence why we opt for shells. It's for the aesthetics, and also they are lightweight structures. We can make them very lightweight but still be very strong. But of course, I mean, the analysis of shells, the fact that they are lightweight, the stability failure becomes a problem. That's why sometimes we get to see engineers being concerned with the buckling behavior, etc. But that's not for today. Today we want to analyze or derive the stress expressions that act in the shell. The stresses, they can act tangential in a way that is ringing around the spherical dome, or probably acting in a upward tangential as the curvature runs through the spherical dome, which will be clear on what I mean by that as we go through this video. Okay, so the weight per unit volume of water is gamma, and the shell is constructed with a metal plate of constant thickness T, and is provided with a flat circular plate closure that is in contact with the lake bed. The enclosure is watertight, air-filled, and maintained at atmospheric pressure and normal temperature for human activities. So for question 1, it wants us to ignore self-weight of the shell and consider only the external hydrostatic pressure, and they say derive the general expressions for the meridional and hook stresses. And I'm going to discuss what are those. Throughout the hemispherical shell, in terms of the angular coordinate phi of the spherical shell, and the parameters gamma, A, T, and H. So it's gonna be fun. All right. So we're gonna, before we just start with this question, let's just go back and get to understand this internal actions acting on the shell element. Okay. So I've taken this snap of the picture. This snap of the picture. I've taken it and I have zoomed it and I've cut out an element out of that just to discuss it. Okay. So we're first going to zoom this in. Okay, so first let's discuss this n theta that you see. So this n theta refers to what we call a hoop stress or hoop forces. They go around this dome, spherical dome. Example, we are assuming that the shell is a shell of revolution and is loaded axisymmetrically. It's important to denote that. Otherwise, if this element of the shell was not loaded axisymmetrically, then we wouldn't be having this type of theory, which is gonna come as I discuss it, which is basically the membrane theory. I can just mention it. It's called the membrane theory. It's the theory that we use in the analysis of shells. So basically, when we talk about membrane theory, it means it's we consider only internal forces acting in the shell. And this internal forces is basically the hoop stress and your meridional stress. But there's no bending in the shell. We do not consider bending, and also the shear moments, shear forces, as well as twisting moments as well. There are no bending, twisting moments, and shear forces, transverse shear forces acting on the shell. Okay, but of course, if it's not loaded axisymmetrically, it's then a different story, which is quite a bit complicated as well. Okay, so now let's zoom in. So as I said, we're going to start first with n theta. So this is n theta, which refers to hoop stresses. So hoop stresses, the theta doesn't change as we go around. It stays constant. So hoop stress, think of hoop stress as a hula hoop. Remember when you were a kid, when you used to play with a hula hoop and you used to move your waist in a kind of rotational movement. And if you could keep that movement, steady, then the hula hoop will keep on going around. But if the moment when you stop moving your waist in a rotational movement, then that hula hoop gravitational force gets to take that hula hoop, and then the hula hoop will just fall onto the ground and you lose the game. Those were the fun times. But now we're using that theory in here. Okay. It's nice because think of a spherical dome. If you look at the spherical dome in plane, what you see is a circle. It's a series of circles or traces of circles. So as you go down, the radius of the circle gets bigger and bigger and bigger, and then that's what you have. So it's a bit of this stack or traces of hula hoops as you go up, meaning as you come from here, as you go up, the radius of the hula hoop or circles, it gets smaller and smaller. Okay, so just a note to make, this hoop stress as you go around, keeping your height the same, it does not change the hoop stress. But as you go up, it gets to increase until it gets to maximum point, which is here at the apex or at the top. That's where you have maximum hoop stress. Okay. Whereas now, if we get to n phi, which is the meridional stress, it does change. Phi does change through the shell element. Hence why you see here it's n phi plus d n phi, which is just it's almost like that dx or dy, but in this sense we're saying with respect to phi, d phi. Okay, because the meridional stress does change as you move along in that tangential direction. And then if you look at R1 and R2, so basically those are your, we'll start with R1. So R1 is the principal, it's basically the radius of curvature, the principal radius of curvature of the shell at any given point. Okay, is denoted by R1, whereas R2 is that second principal radius of curvature of the shell mid-surface, given by the distance between the point in question and the intersection of the normal to the shell mid-surface at that point. Okay, so it's basically that distance between here for R2, that distance between them there, and then R1 is that distance between that point and that point. Okay, and of course, the book by Alphonse Zingoni, it's called Theory and Analysis of Structures. I think it was published in 1999, and I've also referenced it in my previous video. It does describe this also two variables quite more in a sophisticated manner. If I'm not that clear, of course. Okay, so, and then we have these two components, PR and P phi. Basically, these are your external loadings. External loading applied towards the element. So this refers to the components of your external loading. Whereas PR is the normal, it's the force acting normal to the element, shell element, and then this one is the force acting tangential to the shell element, P phi, of course. So we have discussed P, and then we've discussed N phi, and then N theta, and then R1 and R2. And then, of course, you have your R, the big R. That's the radius of the horizontal hoop circle that passes through the origin. The big R. It's the radius of the horizontal hoop circle. So that means if you look at the spherical dome from in plane, and you look at those traces of circles, the radius of the circle there, that's the big R. Okay. And this should be very familiar if you did vector calculus or calculus 3. It should be very, very familiar where you did spherical coordinates and cylindrical coordinates. You remember you had that rho, phi, theta, etc. This is basically the same, exactly one and the same thing. Okay, and then of course, what did I leave? So the angle measured from the axis of revolution of the shell to the normal to the shell's mid-surface at that point in question, it should be the theta. Okay, that's theta, of course. And then we have one angle which is phi. Phi, it's that angle that increases. It starts from the axis of symmetry. I think I did denote it quite visibly here, phi. It's quite important. Sorry. It's quite important, phi. So it's that angle that moves from your, what is it? From your axis of symmetry, from there, axis of symmetry, or it increases as you move away from the axis of symmetry. That's your phi. And I think that's it. So basically, yeah, that's what I've written here. It's basically what I've talked about, that we assume membrane theory in shells. It means shells that are loaded axisymmetrically and shells of revolution, of course. Therefore, only internal forces, which is meridional stress, which is stress acting in that direction, and then the hoop stress, it's acting in that direction. Okay, so whenever you deal with shells and you get to analyze them, those are very important stress resultant to derive. Okay, very, very important, extremely important. And hence why we're dealing with them in this question. Of course, assuming also the boundary conditions are satisfied as well. Okay, assuming the boundary conditions are satisfied. And then, of course, here I just said the hoop stress does not change with respect to theta due to axis symmetry, while the meridional stress does vary with theta, as I've shown you guys. Okay, so all of this piece of theory, together with a series of calculations which are detailed in the textbook that by Alphonse Zingoni et al. And it's called Theory and Analysis of Structures. If you go to it, it's very detailed in the derivation. I'm not going to go through the derivations, but basically these are the governing equations that you get for the meridional stress and then for the hoop stress. Okay, these are your governing equations, and these equations, I could tell you, they are extremely important. they are extremely important in the derivations of this stress resultant, because they fit anyway, whether you're dealing with spherical tank, whether you're dealing with a conical vessel, spherical vessel, ellipse, what is it, elliptic vessel, and vessels that presume that ellipse shape and elliptic shape. It's they fit everywhere. Okay. Of course, this is basically with the assumption that this what is it, the your shell of revolution is loaded axisymmetrically. Okay. And of course, I did denote PR, that's your external pressure applied in the direction normal to the mid-surface. So it's normal. PR is normal to the mid-surface, shell mid-surface, and then P phi, it's tangential to the meridional, meaning it's in the meridional direction. That's what I meant to say. P phi, it's in the meridional direction. Okay, so now, as I said, there are many applications of membrane theory to various shells, like spherical vessel, ellipsoidal vessel, cylindrical vessel, spherical dome, conical dome. They are all different types of shells. Sometimes you deal with, this is in South Africa. I'm sure you guys have seen these silos that presume that type of vuvuzela type of shape, which takes the shape of what do we call it? The shape of a hyperboloid. Okay, because we have various types of shells as well. We have shells that have positive Gaussian curvature, which we call them synclastic shells, and then we have shells that have negative Gaussian curvature, and we call them anticlastic. And that's the type of shell. When I say the hyperboloid of revolution, it's that silo. It presumes that hyperboloid type of shape. Okay. And this you should have done in vector calculus, as I'm saying again. Hyperboloid, paraboloid, elliptic paraboloid, circular paraboloid. You should all remember that type of maths. It's basically shells. Okay. But now, today in this problem, we're dealing with a spherical dome, as I said in the question, which is submerged in the water. Okay, so for a spherical dome, the loading components, basically PR is equals to Q cos phi. And of course, this Q here, it could be the self-weight, combination of self-weight and the superimposed load. Self-weight of the spherical dome itself, or the superimposed load, which is the external load applied. Okay, so in this case here, our external load is what? It's water. It's basically water acting on the spherical dome. But then, as the question said, we are going to ignore the self-weight of the spherical dome. Okay, so in the derivation of a stress resultant, so since it's a spherical, it's a sphere, therefore you should expect R1 to be equal to R2, and we can just say it's A. Okay, hence why you saw that hint here of the radius just being A in this manner. Okay. And if we substitute the above expressions in the governing equation, this is what we get for the meridional stress for a spherical dome. I should very emphasize that, for a spherical dome. This is what we get. And of course, this K here, it's the constant of integration. You remember when you used to do the integration, you integrate, especially for indefinite integrals, you get to integrate and then you have that plus C. It's the same thing here with that constant K. So we get to solve it using our conditions of the boundary conditions of the boundary condition, the support conditions basically. So at phi goes to 0, we get to say the boundary condition, the K constant equals to minus QA squared. So phi 0, that means it's cos of 0, it's 1. And then, of course, you solve for K, and you should get that negative QA squared. Okay, and then if you substitute in K in the equation, you should get what do you get? You should get that this scenario here if you substitute K into the equation. And then, of course, if you further manipulate, which will take you not a long time, but it will really test your trigonometric remember the trigonometric identity scales that you used to do all the way from grade 10. That's where now you get to use quite a bit of it here. So this is the resultant equation that you get for a meridional stress. And of course, this you can substitute in your Hooke stress equation to get your Hooke stress expression. Okay. Of course, this is for a spherical dome generally. Okay. But now, due to the fact that our loading is hydrostatic, as I said, it's water, Q, I did say Q, it's your load per unit area. So Q basically here, it's going to be your gamma, which is your unit weight, multiplied by the height h. If you remember how we deal with hydrostatic pressure, it does increase with height. And of course, it's going to be the unit weight of water multiplied by h. Okay. But in this instant, since we have our spherical dome that is submerged, so h here, it's not basically that whole h. It's going to be h minus a cos phi. So the a cos phi is basically this height. It's basically that height. So it's going to be h minus a cos phi. That's your h in this case. Okay. Hence why I said h minus a cos phi. And then, of course, it's going to be negative. Remember that general formulation. Okay. Because remember, if in the stress derivations, if it's the stress it's acting towards the surface, it's presumed to be compressive, which is negative. And then if it's moving away, it's considered to be positive. All right. So if you remember how water acts, water or the resultant forces due to the hydrostatic pressure, pressure acts normal to the surface. That's what I'm trying to say. Pressure acts normal to the surface. Hence why you see here P phi, which acts P phi, which is tangential. It should be 0 because we know that pressure acts normal to the surface. That's why P phi here is 0. Okay. Because it's tangential and we do not have tangential forces due to hydrostatic pressure. It's only normal forces due to pressure. Okay, so now if you remember our governing equation for our governing equation for meridional stress, it's this piece of whole junk here. So it's that equation here. If I can go up again, it's that equation. I've taken that equation and I've pasted it here. I'm not going to use this equation. The reason why, it's because this is for general loading of a spherical dome. But here we're talking about hydrostatic loading. Hence why we need to go and retake that formula again and resubstitute again. Okay, so please, when you solve or when you analyze spherical domes, you can't just take this general formula. You need to go to the governing, the main generic version of the meridional expression or meridional stress resultant equation, which is this one. You always this is the main engine. Okay, whatever you solve in terms of any type of, could be spherical, conical, you always go back to that. Okay. Of course, if you solve it for meridional stress. Okay, so I took that equation and now I'm going to substitute in for PR. P phi we know is 0. R1 and R2, it's still the same theory. It's a spherical sphere. That means R1 and R2 is the same. Hence why it's A. So I've substituted them here. It's going to be A squared. R1, R2, it's A times A, that's A squared. And then that's R2, it's still A, sine squared. And then, of course, this term here vanishes because P phi is 0. And then we still have sine phi and then d phi. Because remember, I did say the meridional stress does change with phi. And then plus K, the integration constant. Okay, so we further simplify this. Substitute in for PR. Remember what PR is. It's going to be the unit weight multiplied by that height, which is Q. So it's going to be that. That's your PR multiplied by cos phi. and then multiply by sine phi d phi, and I'm still keeping this the same. Okay. And then I further expand this equation. I multiply out my gamma, and then this is what I have. So it's gamma cos phi sine phi multiplied by h, it's that term. And then it's gamma cos phi sine phi multiplied by negative a cos phi. Of course, it's going to be 2 cos phi's, hence why it's cos squared phi, and then a, and then it's sine phi, and then d phi. Okay, so now if you take the integral of each here term, because you can take the integral separately since there's a minus in between. So if you take the integral of this separately with respect to phi, of course, so that means your gamma h here, it's almost like a constant. You can just take it out. So this is what you get, okay, if you take the integral of cos phi multiplied by sine phi. Or if you're not familiar with phi, you want to use x, because some students, when they see x, it's something that is quite familiar with them all the time. You can always put x, then you will see, you can always put cos x and sin x, and to get the same thing, doesn't matter. Same way, if you take the integral of cos squared phi sin phi with respect to phi, gamma a here, it's a constant as well, you will get that resultant. Okay. And of course, I still have my a squared, and then of course that out, what is it, 1 over a sine squared phi, it's still outside as well. Okay, so I'm going through step by step because this is very complicated. It could be it's really complicated. Yeah, it's really complicated. It's maths heavy, very, very maths heavy. Okay, so now if you factor out gamma, because as you can see here, gamma is a common factor, you can factor it out, and then you have gamma a squared, and you're left with minus h cos squared phi over 2, and then it's a cos cube phi over 3, and then plus k. And then of course you solve for the condition of finiteness where phi is equals to 0 in order for you to get that constant k. And then if you solve for k when phi is 0, then you get k to be equal to that. Okay, and then you substitute it in that formula. Okay, so it's basically that piece. I've written it here again, and then instead of k, and then I substitute in for k. It's exactly the same scenario that we did here. Remember, you solve for k was that much, and then I substitute in for k. So I'm doing exactly the same, except now we're dealing with a different type of loading. Okay, so we are here now. So this is what we have. So we can simplify this further, and then we solved for the common denominator, which is 6, and then also it's 6 here, and then that's what I have. It's going to be 6, 6. So this is quite just your maths logic. And then of course I factor out 6 as a common denominator, and then it's there. And then I've also factored it out, phi a squared as well out. Okay, phi a squared. I think I should have put in, because yeah, I should have put in an extra bracket there just to see that this gamma a squared, it goes all through. Actually no, it's correct. The gamma a squared that I took out, it's that one, hence why it's gamma a squared. So it's going to be 2a cos cube phi minus 3h cos squared phi plus 3h, because I've taken out gamma a squared and then gamma a squared as well there as a common factor, which is there. Okay, we can pause the video. Feel free to pause it and to see exactly if I'm moving a little bit too fast. So now we are here. So that's your meridional stress equation. And now we can still simplify this further. And I've let cos phi to be x. So if we let cos phi to be x, so I've taken this expression and I've rewritten it, but instead of writing cos phi, and then I just put x. So it's going to be 2ax cubed minus 3hx squared, and then plus your constant. Okay, and then I resolved it again. I've taken 2a, I've paired it with 2ax cubed, and then 3h I've paired it with minus 3hx squared, and then from there I've taken out 2a as a common factor and 3h as a common factor, and this is what we have there. And then I've further simplified this two terms. This is you can further simplify it to that expression, and then this you can further simplify to that expression. And then you can simplify it any further from there. And therefore, I've substituted in cos phi for x. Wherever you see x, I put cos phi. And then it's all that nasty. Okay, so all that nasty, I've rewritten it again into the original expression, which is this one. I've rewritten it again, simplified. Okay, so now I have distributed in sine squared into the expression. Sine squared, if you rewrite it, you will see that, of course, this is phi here. Oops, sorry. That should be phi there. So sine squared, if you remember its trigonometric identity, I'm talking about this sine squared here, sine squared phi. So if you remember its trigonometric identity, sine squared is equals to 1 minus cos squared, 1 minus cos squared phi. Sine squared phi is equals to 1 minus cos squared phi. And then if you further expand 1 minus cos squared phi, you get 1 minus cos phi multiplied by 1 plus cos phi. That big there. Okay, so this basically is sine squared phi. And then as well here it's sine squared phi. Okay, so as I said, it's quite piece of junk. It's maths heavy, and I understand you can just pause the video because it took me, because actually this is the question that I did with my friend when I was doing this course, and I remember it took us time to actually simplify this further and further to get this result at the end. It was not easy. It was absolutely not easy at all. Okay, so now after you have done that, and then you can cancel the like terms, and then this is what you get here. This is what you end up with. Okay, and that's your equation for the meridional stress of a spherical dome subjected to hydrostatic pressure. Quite a hefty, right? So now that you have got your meridional stress resultant, now you can substitute it into your Hooke's stress equation. So basically that's your generic also, or the governing equation for the Hooke's stress, and that's the equation. So R2, it's A, and then PR, remember, it's gamma multiplied by H minus A cos phi. And then, of course, it's going to be that, which is that. Okay, and then R2 over R1 is simply going to be 1 because they are the same. And then from there, you just have N phi. So basically, this is minus N phi, which is that. Okay, which is your meridional stress. So now we know that, as I discussed it with you, Hooke's stress, it's maximum here at the top, where phi is 0. So that's your maximum Hooke's stress. So that's why you see here I've said N phi, or I mean N theta max, occurs at the top where phi is 0. Okay, so therefore N theta max is equals to, that means I've substituted in phi for 0. If you substitute in for phi for 0 in this equation, this is what you will get. Okay, and then if you further simplify this equation, you will get that. And then if you further simplify again that expression where you take out H minus A is a common denominator, I mean common factor, and then you're going to end up with gamma A minus gamma A over 2, which is gamma A over 2. Hence why we have our final equation for N theta max, Hooke's stress at its maximum point. Okay, so now if you remember, the question said taking gamma as 10 kilonewtons per cubic meter, and given that A is equals to 10 meters and H, which is height, is 20 meters, which is deep. It's quite deep. Estimate a minimum constant shell thickness that will ensure that the maximum compressive stress induced in the shell by external hydrostatic pressure does not exceed 50 megapascals. Okay, so we need to find the thickness such that the thickness of the shell, such that the maximum compressive stress induced in the shell. Because remember, we have this shell is in submerged into water, and The stress is due to the hydrostatic pressure. They're acting normal to the surface of the shell. They're acting all around normal to the surface, and therefore trying to compress that spherical dome. So we need to find that maximum compressive stress that the shell can take. I mean, presuming that the hydrostatic pressure does not exceed 50 MPa. Okay. So basically, now that we have derived that, we can find what we can substitute in H, which was given as 20, and then A was given as 10 meters, and then gamma was given as 10 kilonewtons per cubic meter, and then A is 10 meters over 2, and then this will give you 500 newtons per millimeter. And from there, you can get stress through, because this is your hoop force per millimeter. So if you divide it further by T to get stress, and then this is what you get for T, because remember the stress here, the maximum stress we are allowed is 50 millimeters. I mean 50 megapascals, sorry, 50 megapascals. And therefore solving for T, you should get T as 10 millimeters thick. Therefore your shell needs to be 10 millimeters thick in order to resist that hydrostatic pressure subjected to 50 megapascals. That is insane. That is absolutely insane. It tells you how efficient shells are. 10 millimeters thick is very, very thin. It's thin. It's thin. For a shell that big, it's thin. It's very insane, and that's the power or the efficiency that shells give you. And I hope you really enjoyed this video. Basically, this is it. I'm going to try and do the same thing with this question, but now using finite element analysis. I'm going to use abacus in particular, where I get to derive the hoop stresses and the meridional stresses and get to compare the results. But since it's a shell made out of metal plate, maybe let's just assume it will be a concrete. Therefore, I'll use concrete properties. And let's assume this question is also concrete. Let's scratch that metal, think of it as concrete, okay? And make it more fun and see if we get the same resultant stresses as we have done here manually. And yeah, I think I'll do that in the next video. All right. Thank you guys. I hope you enjoyed. Take care. Bye-bye.